Good morning. Today we will start our lecture number 22. But before that, I would like to ask you to deal with evaluation. I will give you an information that is spot number of the course is EGM 4523C. I don't know what that letter means. Section 001. CRN number 16110, and the course name, of course, is Intermediate Strengths of Materials. Please do that if you did not do that yet. That is one thing. Second thing is I would like to share some things that happened past semester, and in past semester, I'm in evaluation. I got unbelievable evaluation. I usually get very good evaluations, and past semester was unbelievably great. It said, for example, I'm showing off, so to say. It has been a tremendous honor and pleasure to have taken this course with Dr. Elishakoff and Yu Chen Lee. That course is statics that I taught past semester. I felt as though I was studying under Albert Einstein and Wong from Marvel Comics, Doctor Strange. This I don't know, and my TA also did not know who is Wong from Marvel Comics, Doctor Strange. On occasion, Dr. Elishakoff did venture into deep end with explanation of physics through derivatives and integration techniques with the presumptions that the class remembers everything we learned in calculus. But these moments were to be expected. In addition to statics, Elishakoff would at times inject life wisdom during class by suggesting leisure reading material, associating the subject matter with history, or enlightening us on the different labels of scientific representation in different parts of the world. This class is a true gem in engineering curriculum and represents all that is good and wholesome in the spirit of liberal arts and sciences. I strongly endorse its augmentation and propagation. Okay, there was he gives a retake for our worst test grade. Then the student wrote, a lot of homeworks was assigned. Not in this course, however, there are small amount of homeworks assigned. Anyways, one graduate student also sent me a message that I cannot find, but I have it in my office, where he wrote that class that I taught, that is vibrations, was the best class he's ever taken in FAU, or where he did PhD, or in previous university, UTEP. I don't know what university is that, where he got master's. Anyways, thank you for your kind consideration, and you can expect from me kind consideration, surely without any conditions, without anything. That is demanded from me, especially in these trying times for each of us. Now I want to just comment about two questions that I received, and two questions that I received was that just 1 second. No, not in this, not this. In 2020, on page 2020, I derived this expression for maximum shear stress. Okay, we take an element. An element is under plane condition, means all stresses are in one plane. That is sigma x, this is sigma y, then there is tau xy. Okay, they are in one plane. Then tau maximum equals, in terms of initial stress, is sigma x and sigma y, and tau is square root sigma x minus sigma y squared plus tau xy squared. Now, and student was wondering that this was not, as I did in lecture 21, half difference between principal stresses. But if you will go just next page, from 2020 to 2021, I wrote maximum stress in that condition and minimum stress. And I suggested, let us calculate for fun. Let us calculate for fun. You may say, okay, this is not fun. But, okay, let us calculate this. Sigma first minus sigma second. I did not write sigma 1, sigma 2. Sigma 1, sigma 2, sigma 3 are reserved for principal stresses in space. So sigma first minus sigma 2 equals this minus times minus this will be 2 times this expression. But 2 times this expression is 2 times tau max that was obtained on previous page. So tau max equals sigma first minus sigma 2 divided by 2. Okay. Second question that was discussed. Project question. Was, do I need determinants? In problem 1, of project 2. Or maybe, just maybe, there is another way. That is a question. Answer. You surely need determinants. No other way. Known to me. Of course, one can try method of substitution, method of expressing one unknown through others. But this is a tedious way. Good for determinant, good for 2x2 equations, or 3x3, or even 4x4. That is for experienced person. But not for 8x8 determinant. Okay, why 8x8? another question. So it's question 2. It's question 1. Okay. I'll tell you, for example, if we have such a beam, such a column, that is, let us say, I don't know, 33 EI, and that is EI. And then there is this load P. Then when we have to use fourth order differential equation. Unless beam is simply supported, unless column is simply supported. Okay, then for this case, so here we have two boundary conditions. V equals 0, V prime equals 0. Here we have 4 continuity conditions. And that is V on left equals V on right. Then V prime, that is continuity of displacements. I will write down continuity of displacements. V prime left left means to the left of this cross section, just V right, continuity of slopes. Then, look please, let us imagine this is EI1, and that is EI2. Then continuity of shear stresses, EI1, V third derivative equals EI2, V left, V right, third derivatives, continuity of shear force. Then EI1 V left double prime equals EI2 V right double prime. Continuity of bending moments. So the 2 plus 4 is 6. Now we have here conditions, boundary conditions. 2 boundary conditions. And that is bending moment equals 0. EI2 V double prime, so that is at L, equals 0. And then effective shear force equals 0. And that is EI2 V double triple prime L plus P V prime L equals 0. Don't forget this term. I used it for free end. So in total then we get, that is 1. In total we get 8 conditions. In total, 8 equations with 8 unknowns. Okay, a question, how to evaluate, okay, before that, how to proceed? Assume I know how to evaluate determinant. For a moment. You may say, come on, I cannot assume that, but assume for just one moment. Okay, so this whole determinant, let us call it F. Unknown is P. So what we have to solve is this is our equation. How to solve it? Graphically. So I take this, that is P, that is F of P. So I evaluate determinant for P1, let us say P1. So that is P1. You take your value, okay? So then I evaluate FP1. Imagine that is positive. Then FP2, that is P2. FP2. Imagine that is also positive. Then P3. Imagine that is negative. That means that curve behaves, it's not important how it behaves, but main thing is that it crosses this axis. Okay, once you found this P2 and P3, then my recommendation is then to these intervals that you have to cut by 2. Okay, then imagine this average. Calculate there, that is P4. Calculate FP4. If it is negative, that means that root is to the left, etc. Then you proceed and you find this root. So that is graphical solution. Now you need to choose P1. Everyone chooses as he wants or she wants. Now how to evaluate determinant? Main question. Okay, we know, of course, how to evaluate determinant when we have 2 by 2 determinant. Okay, 2 by 2 we know. 3, 4, 5, 6. So that equals 3 times 6 minus 4 times 5. We also know how to evaluate determinant that is 3 by 3. 1, 2, 3, 4, 5, 6, 3, 2, 1. So then we are using Sarius rule. Okay, so this on main diagonal 1 times 5 times 1. Then this plus 2 times 6 times 3. Then plus this one plus 4 times 2 times 3. Then minus terms, these ones. 3 times 5 times 3, etc. Then these ones. But what about 4 times 4, 4 by 4, and 5 by 5? Or 5 by 5? So we go to His Excellency computer. Two ways, MATLAB. So you evaluate, you choose P1, go to MATLAB, evaluate FP1, and you put on your figure. Okay, so FP1 by MATLAB, FP2 by MATLAB, etc. Okay, if you want, you can also evaluate via Maple. You can say, come on, I did not study maple. But it is easy as 1, 2, 3. You are using help in computer within MATLAB. FAU has MATLAB everywhere. On your private laptop, it may not exist. You should go through FAU. And you are using help, you can study this in half hour. I'm promising you. And once you will learn Maple, you will never give up. But MATLAB is also as good. Thank you. I answered these 2 questions that there were. I will put these answers also on, at the end of my lecture notes, I will add this, okay? At the end, not in the beginning, despite the fact that I'm doing it in the beginning. Otherwise, some people maybe don't need this explanation. And therefore, I do not want to start with this, and they may find that maybe I did not give the lecture or something like that. Okay, so we go to 20. So we had 21. Yeah, I think that we covered 17 pages, 21, 17. Okay? So let me show you this. I think we covered until page 17, 21, 17, which is second theory of strengths. Second. Maximum linear deformation criterion, okay? Again, second criterion. I wrote specially this theory because to, again, give up this notion that it is a theory. It is a criterion. It comes from the head of someone. I will give you later towards the end historical background who gave what, just for you to know. And also it is good this knowledge to be exhibited to your boss when you are working in the company. It makes also, develops a culture in the company of knowing who did what and where does it come from. Okay, so we have this situation where we have principal stresses, sigma 1, that is sigma 1, that is on vertical, that is vertical. Sigma 2 horizontal and sigma 3 also horizontal. Now this state, do you remember, we say that that is our state. That is hypothesized state in uniaxial direction. In uniaxial direction, we know experiments, okay? And we conducted experiments, we know sigma yield, and we know that that is sigma allowable, okay, through safety factor. So what we say, according to this theory, maximum linear deformation in this element and maximum linear deformation in this element are equal. So here in direction 1, we have 1 over E sigma 1 minus nu Poisson's ratio sigma 2 plus sigma 3. Then there is epsilon in direction 2. 1 over E sigma 2 minus nu sigma 1 plus sigma 3. Epsilon 3, sigma 3 minus nu sigma 2 plus sigma 1. But this is maximum of all. Why? Because this sigma 1 is biggest of sigma 2 and sigma 3. So epsilon 1 here equals to epsilon 1 there. So 1 over E, sigma 1 minus nu sigma 2 plus sigma 3 equals sigma equivalent over E. From here we get sigma equivalent. Sigma equivalent is sigma 1 minus nu sigma 2 plus sigma 3. Okay, now principal stresses. So I'm just showing you again, just simpler, not simpler, but explanation again, principal stresses. In original axis, we have various stresses, and I left this out to fill now. So there is this sigma z, there is sigma x, then there is sigma y, then there is tau, tau, that is shear stress. First, I give to what this face is perpendicular to z. Second index is direction, that is y. Then there is another one, that is tau, again z, but in x direction, etc. So there are many stresses. We can show that this, if we are rotating coordinate systems, so there will be some coordinate system where shear forces will not be present. Okay? So sigma 1, sigma 2, sigma 3. Shear forces are not present. Just say no to tau. That is like Shakespeare's Romeo and Juliet. Two families, Capuletis and Montagues, are enemies of each other. Romeo is not invited to Juliet's party. Okay, so here just say no to Romeo if you want, or tau. So no shear stresses here. Then we have only normal stresses, sigma 1, sigma 2, sigma 3. They are called principal stresses. And biggest principal stress of them is sigma 1, smallest is sigma 3. Whatever is left is sigma 2. That is 22, 1. Okay. Okay, then 22, 2. How to find sigma 1, sigma 2, and sigma 3? Okay. Okay, pay attention. In original state, we have sigma x, tau xy, tau xz. So tau yx, sigma y, tau yz. Tau zx, tau zy, sigma z. So what we do is we subtract sigma, just sigma, from diagonal elements, and we consider this determinant. So then we get determinant. See, determinants again show up. That is like Romeo shows himself in the party of Juliet. Okay? Okay, then we can calculate easily. Sigma x minus sigma times sigma y minus sigma times sigma z minus z. Then these elements, product of these two, by this. Tau xy, tau yz, tau zx. Then this, tau yx, tau zy, tau xz, etc. Then these elements, minus this, tau xz, tau zx, sigma y minus sigma, etc. Okay, we get cubic equation. Why? Because look, there is sigma, sigma, and sigma. We get cubic equation, so it has three roots. Sigma first, sigma second, sigma third. I'm using Roman notation. Why? Because 1, 2, 3, I will be using for something else. Then sigma 1 is a maximum. So solution usually is numerical, usually. Numerical solution. okay? Of course, there is formula for cubic equations. There is a solution by Cardano's formula. Do you remember Cardano, who was born in 1501? He was an astrologer and predicted that he will die in 1576. Day comes and friends ask him, Cardano, you're the greatest scientist of everywhere, of entire planet. And you could not predict. He takes a poison and dies. That is terrible. We are different from Cardano. We stay at home in order to fight coronavirus. Okay, then we find it numerically or through Cardano's formula. But it's better to find numerically because we have a computer. There was no computer before, and people used Cardano's formula. Now we can go to His Excellency's computer and get the results. Now computer works for us. Okay, we have a personal assistant, computer. So sigma 1 is a maximum. Sigma 3 is a minimum of these three. And whatever is left, the third one, is sigma 2. Not max, not min. Okay, 22.2. Now will be 22.3. Yeah, I thought that I will cover this past time, but therefore I numbered, maybe prematurely. I should have numbered. Probably in the future I will not number any pages ahead of time. Okay, now there is another criterion. Maximum shear strength criterion. You may say that sounds very strange because we worked so hard not to have shear stress. Sigma 1, sigma 2, sigma 3 are here. Now we suddenly say maximum shear strength criterion. Most unfortunately, I could not find in my drawers any chalk. And because here, usually we had chalk here, and I could just pick up the chalk. So if you take this chalk, okay, and you twist it, okay, in opposite directions, this chalk suddenly will chalk. So we take this chalk and we twist it like this. Okay, we increase the force, increase force. Okay, then at some point this chalk will break. Then I would ask students, where does it break? I was asking students, do you think it will break? They said, of course, you are a strong man. Where will it break? Okay, nearly middle. How? Okay, usually the breakage was happening like this. Look, please. Okay, here in some approximately, I would ask students, what is approximate angle? Approximately, they would say 45 degrees. Oh, then I say, look, please, not maximum stress decided, but something else decided. So shear stress decided. Okay, that is 22.3b. So I'll write A. Okay, then two stress states are equivalent to each other if they share the same maximum shear stress. So maximum shear stress will be acting in this plane, sigma 1, sigma 3. And it will be sigma 1 minus sigma 3 divided by 2. Here, maximum shear stress, there is just one direction. It will be sigma equivalent divided by 2, because the 3 equals 0. So we are equating these two, and we get sigma equivalent equals sigma 1 minus sigma 3. Tresca. I think Italian meant Tresca's yield condition. Tresca says, pay attention, what is the difference between all these criteria? Let us start with 1. First criteria was maximum normal stress criteria, that is sigma 1. But then we said, come on, there is no sigma 2, there is no sigma 3. Are they unimportant? Are sigma 2 and sigma 3 second-class citizens? Or let us say, yes, in that theory they are considered unimportant. Here suddenly sigma 3 is unimportant, but sigma 2 is not important. But at least that is an improvement. Improvement over sigma 1 criterion, because suddenly sigma 3 plays some role. We will get to the place where 3, sigma 1, sigma 2, and sigma 3 will be playing a role. Actually, today, when we discussed this criterion, maximum linear deformation criterion, here all 3 are present. They are all invited to the dinner. So the main thing, which one to adopt, is experiment. Okay, and accumulated experience, approximately of 100 years. Not more than that, I would say. Approximately, I said, 100 years of experience we have. But humankind, for 20 centuries, so to say, did not know this. Oh, why 20? For millions of years, did not know this. Okay, this page we don't need at this moment. Now we will deal with some other issue, which is 22.4. In order to get where we want to get, we need to consider volume change, the notion of volume change. Look, please, we have this or sigma 1, sigma 2, sigma 3, or sigma x, sigma y, sigma z. They are the same because there is no tau here. So epsilon x equals sigma x over E minus nu times sigma y over E minus nu times sigma z over E. Let us consider fun again. Let us sum all of these stresses. So then we have sigma x, so will be, look please, sigma x here, sigma x here, sigma x here. So sigma x appears once, but then it is multiplied by, that is 1, but 2 times, okay, nu, minus nu and minus nu. So minus 2 nu over E sigma x. The same is sigma y. Sigma y will be here with 1, this 1. And sigma y appears here and here, so minus 2 nu. And then sigma z appears here, that is 1, and then here and here. So then, let us calculate volume change. So these deformations actually is connected with changing of volume. Okay, let us illustrate this. In the beginning, the volume was dx times dy dz. That is initial volume. Dx changed by deformation. dx 1 plus epsilon x. So that is the value, and then deformation. dy changed into dy 1 plus ey. dz changed 1 plus ez. Pay attention, you had to study this in strength of materials in the previous course. That is part of curriculum. However, I'm repeating it because who knows, maybe you did not study. And even if you did study, then it is a repetition. So then v prime equals nu will be product of these three things. dx, so that is a new length. So that is dx prime. That is new length in y direction, dy prime. That is new length in z direction. So that is then dx 1 plus epsilon x, then this one. That is dy. 1 plus epsilon y, and dz 1 plus epsilon, the product of these three. So then volume comes out, dx, dy, dz, previous volume comes out. Then what we have is 1 plus epsilon x, 1 plus epsilon y, 1 plus epsilon z. Let us subtract from the new volume, previous volume, v prime minus v0. That is then v0, so that is this new volume, v0, 1 plus epsilon x, 1 plus epsilon y, product 1 plus epsilon z minus v0. Okay, and let us relative volume change. V prime minus v0 over v0 will be then, look, that is 1 plus epsilon x, 1 plus epsilon y, 1 plus epsilon z minus 1, because v0 was taken out, and we divided it by v0. So that is what is staying. And then, look, this 1 times 1 times 1 is 1. 1 minus 1 will get 0. Then there is a sum, epsilon x plus epsilon y plus epsilon z when I multiply. And then there are some other small terms, like epsilon x times epsilon y plus epsilon x times epsilon z plus epsilon x, epsilon z. Then there is epsilon x, epsilon y, epsilon z. These are all small because deformations themselves are small. Product of small quantities is much smaller than sum of the quantities. Okay? So 22.4, 22.5. Okay, then pay attention. So, because that is from previous page, I will say, previous. Then epsilon v prime minus v0 over v0 equals epsilon x plus epsilon y plus epsilon z. Then I can calculate from here, I can sum up, and that is what I obtained already. That is 1 minus 2 nu, 1 over e, sigma x plus sigma y plus sigma z. Okay? Did you write? I'm sorry that you are not sitting here, and COVID-19 affected us so much. It separated us, but we are together. You are in your homes, without music, without TV, without movies. I very much hope. I'm watching you virtually. No, I'm not watching you. I'm just saying that I'm watching jokingly. Okay, now if all stresses are positive, means all tension, then naturally that volume increases. Then volume should increase. Volume change should be positive. That means that 1 minus 2 nu should be positive. Okay? If these guys are positive, then this guy is positive. This is positive. So this should not be negative at least. 1 minus 2 nu is 0 or positive. Or 1 is bigger than 2 nu, bigger or equal, or nu is smaller or equal than half. Okay, that is Poisson's ratio cannot be more than half for isotropic materials. Now, what is isotropic materials? I have a sheet, then I'm taking this specimen, and this specimen, and this specimen, and then I'm subjecting them to the tests. Then I get this E1, generally speaking, E2, E3, okay? That is this in this part. And then isotropic means E1 equals E2 equals E3. N is a constant, okay? Material parameters are constant in every direction. Material constants are material parameters are constants in every direction. For isotropic material, so I wrote, for isotropic material, Poisson's ratio cannot exceed half. Now, what is, okay, cannot exceed half? What happens when it equals? Question. What happens when nu equals half? Okay, then change is 0. Volume change is 0. Means that we are extending in every direction, then matter, but volume does not change. So we should say that such a material is inextendable. This is inextendable or incompressible material. Nu equals half. We will remember this. Okay, we will put it in our brain. We will need this information. Any questions? Okay. Now I will, so pay attention, until now we had how many theories? Maximum normal stress criterion. How many theories? How many criteria? Until now. Maximum stress how did we call it? Maximum linear deformation. Then maximum shear stress. Okay, that is 1, 2, 3. Now we will, okay, so here only sigma 1. Here is sigma 1 minus nu sigma 2 plus sigma 3. Here is sigma 1 minus sigma 3. That is sigma equivalent. So here there is only sigma 1. Here is all 3. Here is 2. Now we will introduce fourth criterion, which we will not adopting. But in order, and there will be fifth criterion that we will be adopting. But in order to get to fifth, we have to deal with fourth. So that is 22.8. Energy-based criteria, okay? Or a beautiful theory killed by an ugly fact. So that was called actually Thomas Huxley. British biologist. He said, a tragedy of science. A beautiful theory killed by an ugly fact. So we will deal with such a theory. What we mean here that science is based upon many various theories. Some theories do not satisfy experiments. Such theories are thrown away. What he says they are killed, so to say. We just throw them away. We discard them. We don't use them. Okay, 22.9. So in this particular case, so that is Beltrami. Beltrami is an Italian engineer. Beltrami's criterion. Okay, that is 22.9. So look, please. We have this coordinate system. And in this, so that is y and that is z. And in x direction, there is some sigma x acting. Force, so there is a force. What is a force? That is a stress. So that is, look please, in x direction, that is dx. In y direction, that is dy. In z direction, that is dz. So sigma x acts upon the area dy times dz. So there is a force. That is a stress. Stress is a force over area. So in order to calculate the force itself, we multiply the stress by the area. Force sigma x times dy dz represents an external force for this parallelepiped. So that is this parallelepiped. Change in potential energy of deformation. So as a result, this element accumulates some energy. Change in potential energy of deformation numerically equals the work conducted by external forces. There is no other way. We don't have, in this case, friction or anything else. We consider ideal situation. Hence, the potential energy accumulated by this element numerically equals to the work performed by this force. So let us say, I denoted here sigma x, but we will take sigma 1. du equals 1/2 y1 half of it. Sigma 1 divided z, and it is along, we will have dx will change into, with deformation, will be epsilon 1 dx. That is elongation. So we get 1 half sigma 1 epsilon 1 dx divided dz, which is a volume. Volume is present there. Why 1 half? So we are increasing sigma from this from 0 value to this value. And epsilon changes from here to here. Okay, therefore, that is this work. Work equals integral. Or area. So then, that is a volume. So what we get actually is potential energy, du, equals 1 half sigma 1 epsilon 1 dV. And that is density of potential energy. Density, that means potential energy per volume. Look, please, there is no book anywhere in any language which introduces this topic as I'm introducing. Because I would like you to understand rather than give you a recipe. And that is how it is. That is how usually done. So, then energy, which is potential energy per volume, equals sigma 1 epsilon 1 over 2. Or if I substitute instead of epsilon 1, sigma 1 over E, that is Hooke's law. Thank you, Mr. Robert Hooke. You see, I told you already the story, that Robert Hooke contradicted in one issue to Sir Isaac Newton. Sir Isaac Newton was a president. Okay, he did not do what Pythagoras did. He did not say, throw him overboard from the ship. But what he said there, as a member of Royal Society of England, Robert Hooke's portraits were in various places in Cambridge, in city of Cambridge, in Cambridge University. So Newton ordered all portraits to be burned. Great people sometimes are not very nice. We learn it many years later. So potential energy density equals then sigma, okay, I substitute this here. We get sigma 1 squared over 2e. This 2 is coming, that area equals half. So that is this epsilon 1. That is this sigma 1. So half of this times this is area. Yeah, I did not number this page. I will do it immediately. 2210. Then 2211. If all stresses, assume no shear stress are acting. If all stresses are present, then potential energy change will be 1 half, not just sigma 1 epsilon 1, but also sigma 2 epsilon 2 plus epsilon 3 sigma 3. Okay? Then I have to substitute epsilon 1 equals 1 over E, sigma 1 minus nu sigma 2 plus sigma 3. That is generalized Hooke's law. So Hooke's law was given by an Englishman, Hooke, and this was given by a Frenchman, Poisson. So two guys over the English Channel gave us this law. So then what does that mean? When there is sigma 2, okay, then there is deformation also in x direction. It becomes shorter. So that is minus nu sigma 2 over E. Shortening in direction 1 is proportional to the elongation in direction 2. Any questions? Oh, you see here something. I'm just using used pages to save planet. I don't want to use unused pages, if it is possible. Okay, then what we get here is 2212. Epsilon 2 equals this. 1 over E sigma 2 minus nu sigma 1 plus sigma 3. Epsilon 3 equals this. I substitute everything here, all these formulas here. So look please, sigma 1, then I substitute epsilon 1. Sigma 1 minus nu sigma 2 plus sigma 3 over E. Plus sigma 2, epsilon, sigma 2 times epsilon 2. Sigma 2 minus nu sigma 1 sigma 3 over E. Sigma 3 times sigma 3 minus nu sigma 1 plus sigma 2 over E. So everywhere is sigma 1 squared, sigma 2 squared, sigma 3 squared. So there is 1 over 2, and there is E. So 1 over 2E. Sigma 1 squared plus sigma 2 squared plus sigma 3 squared. Minus nu. Now minus nu. Look please, sigma 1 times sigma 2. Then plus, but there is minus. Sigma 1, sigma 3. Then there is sigma 2 times sigma 1. Then sigma 2 times sigma 3. Then sigma 3 times sigma 1. Sigma 3 times sigma 2. Then we get sigma 1 squared plus sigma 2 squared plus sigma 3 squared. That is here. Then minus nu, but pay attention. Sigma 1, sigma 2, and sigma 2, sigma 1 are the same. So will be then not just nu, but 2 nu. Analogously, these are two the same. Sigma 1, sigma 3 equals sigma 3, sigma 1. And these guys are the same. So will be minus 2 nu and sigma 1, sigma 2 plus sigma 1, sigma 3 plus sigma 2, sigma 3. That is this. Now I think the next page comes from this book. Okay, we finish this derivation. 2212, 2213. I will write down here, 2213. From Norton's book, Machine Design, Integrated Approach. (2213), 2214. Okay, so here we need some phrases only. Historically, several theories have been formulated. Oh. Okay. Historically, several theories have been formed, but not theories, but criteria, yes? I'm revolted by the word theory because no one can with some theory and explained why is that. That was a suggestion of these people. To explain these failures, the maximum normal stress theory, okay, that is one. The maximum normal strain theory, that is two. Then total strain energy theory and distortion. Okay, so that is three. Maximum shear stress, that is three. Okay, there is now two coming. Total strain energy theory. Total strain energy theory is like this. I will write it down. Total strain energy criterion. Beltrami, Italy, 1885, as far as I remember. I was not there, by the way, when this was discovered. I'm not that old. So, what he says that there is this situation, sigma 1, sigma 2, sigma 3. And there is this situation, sigma equivalent. Two conditions are equivalent to each other if total stored potential energy densities equal to each other. Okay, here this equals 1 over 2e, sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 nu, sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 1 sigma 3. Here it equals 1/2 sigma equivalent squared, 2e. When they equal to each other, then we get, from there we will get sigma equivalent squared. Sigma equivalent squared equals sigma 1 squared plus sigma 2 squared plus sigma 3 squared minus 2 nu, sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 1 sigma 3. Or sigma equivalent equals square root sigma 1 squared plus sigma 2 squared plus sigma 3 squared minus 2 nu, sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 1 sigma 3. Okay, so that was done in 1885. 2214, 2215. Experiments did not support. Okay, this criterion looks very nice. All three looks nice. All three sigmas are included. Okay. Looks very nice. People were very excited. Experiment did not support this criterion. Okay, I will describe the experiment. Any questions? Pay attention, I'm not going too fast. We have 9 more minutes left. 22:15. 22:16. Experiment. Okay, so there was some very small element taken. Okay, and placed in water. So that is this element. And that is water. And this element was pressed harshly. Okay? Bridgman. I think Bridgman. Yeah, PW. USA. Okay, American experiments. Okay, so pay attention. If that is, so that is hydrostatic pressure. Pressure from all sides. So sigma 1 equals, so that is this, look. This, and this. So sigma 1 equals sigma 2 equals sigma 3 equals minus P. Okay, if this criterion is correct, when should the element fail? When should have the element failed? So that is when, pay attention. So sigma equivalent equals square root sigma 1 squared, which is minus P squared, plus minus P squared, plus minus P squared, minus 2 nu. Sigma 1, sigma 2, minus P times minus P, plus sigma 2 times sigma 3, minus P times minus P, plus sigma 1, sigma 3, minus P times minus P. That is a square root. Okay, then we will get here, will be 3P squared, then minus 2 nu. That is also P squared, P squared, P squared, 3P squared. Okay, that equals P squared, P, 3 minus, 3 is also square root of 3, and square root 1 minus 2 nu. Okay, then this should be equal, that is sigma yield divided by safety factor, required safety factor. But there is but. But element did not fail at this stress. Means, look please, P equals, from here, sigma equivalent, sigma y, yield stress, divided by 3, 1 minus 2 nu. Okay, and 1 over k required. Did not yield, so we can calculate, that's very easy to calculate, that is sigma yield. Any questions? Okay, Bridgman. $22.17. Okay, so look please, Bridgman. United States comes into play as a young country. Okay, where is it? Yeah, subjected water ice to 1 mega psi hydrostatic compression with no failure. The explanation is that uniform stress in all directions while creating volume change and potentially large strain energies cause no failure. So which means that, look please, by the way, analogous, that is in 1930s. Experiments were conducted. And next page, I think he mentions, that is 2216, 2217. Also another person, Dan Hartog. Dan Hartog. Dan Hartog. He is Dutchman, Netherlands, and USA later. He arrived to the United States in 1924 from Netherlands. By the way, I'm writing some paper, historical paper, and I contacted Dan Hartog's son, who passed away 1 year ago. Actually, he sent me his answer to my questions, and then, after several months, passed away. Recently, from his granddaughter, Dorska, who lives in New Hampshire in the United States, sent me albums, whole albums, of Dan Hartog. I wrote her that I will copy what I want and I will return. She said, no, I loved your article so much. That is a gift from us to you. I will bring that album and I will show you a couple of pictures of Jaap Den Hartog. So he also describes the condition of rocks in great depths in Earth's crust, where they withstand uniform hydrostatic compressive stresses of 5,500 psi over mile of depth due to the weight of rock above. Look, please, sometimes you don't have to do experiment, you just have to think. Okay, and then you are getting the answer to your questions. So therefore, just to sit down and think is the best way of solving some problems by reflection. I think, therefore I am. This is in excess of their typical 3,000 psi ultimate compressive strength. Look, yield stress is 3,000 psi, but they undergo hydrostatic pressure